Let's apply the solve a simpler problem strategy of problem solving using Polya's problem-solving process in the context of a geometry problem. Imagine that you're an architect. You've been asked to build a border for the pond in a local park. A diagram of the pond is shown below. You're told that a 40-foot rope separates the kids' pool from the rest of the pond. That's this rope right here. In addition, two walls of equal length, A and B, shown here, 60 feet each, meet at a right angle, walling off the goldfish habitat from the rest of the pool. So this part of the pool is walled off, and goldfish live here. We apply this information to the diagram. There are two walls of equal length, 20 feet each, and a 40-foot rope separating the kids' pool from the rest of the pond. We also know that the two walls meet at a right angle. So this is a right triangle. Now that we understand the geometry, we strategize. How are we going to figure out the dimensions of the pond? That is, the perimeter around the pond, which will tell us how much wall we're going to need to build. Well, one way to do this would be to measure. We could do this using a yardstick, a measuring tape, or applying the scale of a map to the pond. We could even use a pedometer. If we know the distance of our steps, we could walk around the pond and see how long it takes us to walk around the pond in distance terms. We could also calculate. If there were a formula, we could use a formula to calculate the area, the distance or perimeter around this shape. Or we could simplify. You can probably guess from the title of this module what we're going to do. If we think about how to simplify this, we can really break this pond into two shapes. One is a rectangular shape. We know that it has the bottom border of the rectangle has a border of 40 feet, and we don't know this length here. We also know that we have a circle, or semicircle, that's the kids' pool, with a diameter of 40 feet. Now, it should be clear to us that these are assumptions. We're not actually told anywhere on the diagram or in the specifications that this is a rectangle. It looks like one. It looks like these are right angles in the corners, but we can't be sure. It's an assumption that we have to make. Similarly, we don't know for sure that this kids' pool is a semicircle or half circle. It could be some portion of a circle that's larger than a half circle or less than a half circle. So we are estimating here. We're making a guess based on the assumption that this pond and park map is drawn to scale. With that assumption in mind, we calculate the perimeter of the pond by calculating the perimeter of these three sides of the rectangle and this half of the circle's circumference. Let's look at the rectangle first. Since we are assuming that all of the angles of this rectangle are right angles, then we know that the northern side is 40 feet, just like the southern side. As for the east and west sides, we recall that the Pythagorean theorem states that the square of the first side of a right triangle summed with the square of the second side is equal to the square of the hypotenuse, or the longest side of the right triangle. Here we have two walls of equal length, 20 feet. So 20 squared plus 20 squared is equal to the square of the length of this west side. Or 800 is equal to the square of the length of the west side. If we plug this into a calculator, we find that the square root of 800 is 28.3. And because we only have two significant digits here, 2 and 0, we have to round to 28. So we assume this side length is 28. Since the length of the west side is 28, and again we're assuming that this is a rectangle, we say that the length of the right side is also 28. Now let's move on to look at the circle. We know that circumference is equal to pi times the diameter of the circle, where the diameter is a line that goes through the center of the circle and connects points on opposite sides. We know our diameter is equal to 40 feet. The circumference is equal to pi, 3.14, times 40 feet, or 125.6 feet. So the circumference of the circle, or the perimeter all the way around is 126 feet. But we're only looking at a semicircle, or half of the circumference. So we multiply the circumference by 1/2, or 0.5. 0.5 times 126 is 63. So this area here has a perimeter of 63. We put all of this information together to sum all of the sides to get the perimeter of the pond. Recall the east and west sides are each assumed to be 28 feet, the north side is 40 feet, and the semicircle is 63 feet. So the perimeter is 28 plus 28 plus 40 plus 63 feet, or 159 feet. Let's look back. Recall our assumptions. We assume that the pond is drawn to scale, that we have right angles in our rectangle, and that we're looking at a true semicircle, not more or less than 180 degrees on the circle. What is the impact of these assumptions? Think about it for a moment. Well, if the park is not drawn to scale, we could have a perimeter that's vastly different. For example, the scale could really be anything. And we have some sense that the park is perhaps not to scale. For example, take a look here. This rectangular area looks almost like a square, and yet we're told that the east and west sides are only 28 feet, while the north and south sides are 40 feet. This would indicate to us that the east and west sides are only about 3/4 as long as the north and south sides, but they look exactly the same. So we should be wary of the assumption that this map was drawn to scale. But in any case, it's an estimation. It's the best we can do without actually going out and measuring or getting a better scaled map. We can also think about what else we can calculate. Now that we have the length of these sides, we could calculate, for example, the diagonal of the entire pool. This greater level of specificity gives us a lot of power, if these assumptions were indeed correct, to make a lot of architectural changes to the pool and do a lot of planning without any additional information. This shows the power of using the simplify the problem-solving method. We didn't have to go anywhere. Just sitting here at our desk, we were able to calculate everything we needed